But there is some parallels. There are some parallels between my notes and his notes. But I don't know if I don't think I might end up following much of his. I mean, there would be some developments in his book that would be helpful. And you can certainly use what he has in there. But sometimes, I guess we might have different notation, different problem sets, maybe. But you have it. It's actually fairly complete. I mean, he has a lot of topics.
It's big enough.
Yeah. I don't think. I don't think we have equal notation. That might be the problem. But should not restrict you. Yeah, it's hard to come up with a satisfactory nonlinear book because you start putting a lot of topics there and becomes a catch-up all, and then the book starts growing very fast. So what I have done for myself is just to limit it to, say, topics that we can explore in demos and spend time with the demos, and then have the notes as a support for the concepts. They are not. I tend to write very succinctly. There's not a lot of explanation going on there, but kind of like good enough. But Bernardo's book has really complete explanations, except for the notation in the equations. That would be a really good reference.
So your notes are enough?
My notes should be enough because I'm extracting all the problems from the notes. Yeah. Okay, so is that it? Are we complete? What we are doing here. There is an interest in the department to develop a good archive of demonstrations, physics demonstrations, and this particular course has a lot of demonstrations. So we are going to try this to film the class. Then Jean is going to have a substantial amount of editing time to do, and because obviously there is a lot of things that he has, a lot of comments that he has to suppress, for mature audiences only, and so but he's going to be here, and hopefully it's not in your way. Is everybody's okay? So I'm going to try to be to ignore that the cameras are there and to act normal. So should I wear dark glasses or not? Anyway.
You were on Bernardo's video.
Huh?
The one that yesterday they sent one of the new videos from Mr. Bernardo.
Yeah.
You were on the video.
I was?
Yeah.
What was that video about, remember?
About the electroacoustic.
Oh, yeah, okay.
It was very good.
He's good. Yeah, I mean, there was a script there. He was reading a script. I don't know if you noticed. He was very rigid, paying attention to you were rolling the script, were you not? No?
He doesn't want to do that. He doesn't like the teleprompter, which he needs to do the teleprompter because he looks up above the camera, so kind of awkward, right? So we're working on it.
So, but he's reading something.
Yes.
How is he reading
so
that?
Right now, 17 by 18, large cards.
And you hold them, or?
So they're posted up above the camera.
Okay, and then you just slide them off.
Yeah.
Are they? Did he put out the cover, the plastic cover? What, are they laminated? I mean, that is. Yeah, they should be laminated. Okay, edit all that. That's for mature audiences only. Okay. Anyway, so we are looking at this equation, and one of the very first things to do when once is that for the first time is to try to just bring knowledge, the ready knowledge that one has in solving the linear problem. So that is the first reaction, and we're gonna go through the steps and the mechanics or doing the iteration procedure, and then to find out that it's not good, it actually fails very quickly. So, and then we have to realize from there what is wrong. So this is the idea. The idea is that we imagine that this term is a perturbation to that term. And I'm going to show you a demo where you say, yeah, of course. I mean, it's the pendulum. The pendulum would be the demo to show that in these nonlinearities can be considered as a perturbation to the linear effect. When you look at a pendulum, the linear regime, where the pendulum is can be described by the left-hand side of the equation and the right-hand side being approximately equal to 0. Let me show you how about what angle? About that angle. You know, if you start going beyond that angle, then nonlinearity start coming in. But you would not be able to tell what's the difference between this guy, as it is right now, or that guy, right? So what measures the difference between the small amplitude pendulum and the large amplitude pendulum is their period of oscillation. So it takes the larger the amplitude, the longer the time it takes for the pendulum to go back and forth, right? So we'll discover that effect. There is another demo right here that is the opposite. In this demo, does it look familiar? I'm going to make it oscillate back and forth, up and down. Does it look familiar? This is your homework problem, right? 2 springs, one here, one there. I mean, I'm using 2 on this side, but that has to do mainly with the design of the demo and the fact that I want to prevent this kind of motion. This motion is prevented by having this arrangement of the springs. So the only possibility for this system to oscillate is up and down. So almost in a vertical plane. Almost, I say. Now, this oscillator is nonlinear also. It's linear for small amplitude, but becomes nonlinear for higher amplitude. Now, in the case of the pendulum, it takes a longer time to go back and forth in one cycle, right? It takes one cycle. The larger the amplitude, the longer it takes. In this oscillator, it's the opposite. The larger the amplitude, the shorter the time. We'll see that. We'll also discover that. But today, I just wanted to show you your homework and show you an example of an oscillator where as you increase the amplitude, the period of oscillation decreases. We are going to get to that result today. Yes?
There's a speaker there also?
Yes.
But that's for another thing.
No, that's for the future demo. This actually is gonna be with us for a couple of lectures. The speaker makes this point of support oscillate back and forth. So in this system, we have now a driven system. Okay, so we're going to study driven, damp, nonlinear oscillators with this guy. Okay, so what is, when we go back here, so again, we use, the first reaction is to use an iterative approach to find the solution. And we say, well, let me write X is going to be the first order term, then a second order term, and so on, higher order terms, where I'm imagining that, say, x1, the modulus of x1 is much bigger than the modulus of x2. That's what I'm imagining. Okay, so that I'm correcting my knowledge of the behavior, the linear behavior, by adding terms, and it is such that x1 is the solution to the linear problem. That one. So this is my starting point. I know the linear problem. That's the only problem I really know. So I have to solve very well for the harmonic oscillator, and I'm going to start from that base. And then I'm going to bring in the next correction. So what is the next correction? Well, x2. So what would that be? So let me put it in here. x2 double dot plus omega squared x2 equals to what? Well, equals to the first correction due to nonlinearities. Okay, so if I know the first order problem, and I want to find the second order contribution, this cannot be anymore. Again, it cannot be again equal to 0, right? It has to be equal to what I already know for the linear problem. But this is my equation. This is my equation. So how should I write it? I write it like this. X cubed would be what? x1 plus x2 plus etc. cubed, right? That's what x cubed is. If x is all this, well, x cubed is all that. So leading order. So, or rather, let me start working it out. So what is the first term? That is x1 cubed. Yeah, that's. Then I'm gonna have 3x1 squared x2. Yeah, and then I'm gonna have the other terms. The higher the number here, the smaller the contribution. So let me keep it up to there. But because I'm dealing with the linear problem as my basis, I can imagine x1 itself to be a small quantity. Like for instance, in the case of the pendulum, the linear pendulum is a pendulum that has a small amplitude, right? So if I'm going to explore the nonlinearities of the pendulum, in terms of the linear problem, I have to continue imagining that the x1 term is small. So when I do a cubic expansion, first of all, this guy is smaller than that guy, right? Can you see that? Because the rest of the terms are even smaller, right? The next term would be this guy square and that guy linear. And the next guy is going to be this guy cube. And so I can start neglecting the higher order terms. So but look at this guy. This is x1 squared multiplying x, or rather, yeah, x1 plus 3x2, right? So under this condition, I can drop that term. I can drop the second order term because compared to the first order term, the second order term is very small, right? That's the statement over here. So the cubic term only picks the first contribution, x1 cubed. So if I say x2 is the correction to the linear theory, then what equation does it obey? The linear theory obeys this equation. The correction due to nonlinearities would obey a different equation. What is it? x2 double dot plus omega naught squared times x2 equals to, what do you think it would be? Let's try this. Alpha x1 cubed. The first term, right? So if the linear theory is equal to 0, the next correction should bring in the knowledge of linear theory. Alpha x1 squared. Now I know this because I know the solution for this problem, right? If I know this, I can plug it in there and solve the problem for x2. So that is the iterative approach. You solve the linear problem, you go to the next correction, and this would be the next correction. So if you wanted to do the next order correction, right, the x3 problem, then that x3 problem would look like this. It would look like 3 alpha x1 squared x2. That's how the next order problem will look like. And you can continue the iteration like that. You see what is going on? You know how to solve the harmonic oscillator problem, the linear harmonic oscillator with no forcing and no damping. You know how to solve that one. Then the second order term would be the correction, but it's corrected in terms of you already known solution. The third order term is going to be the next order correction, but it's corrected in terms of the first order and the second order solutions, which already you can actually solve for. So the iterative problem gets you the correction of the behavior of the oscillator in terms of higher harmonics. So let's stop over here and let's see what that generates. So for the linear problem, if x1 obeys this equation, then I know the answer. x1 should be of the form some amplitude A cosine omega naught t plus some phase. That's the most general solution to the harmonic oscillator problem. Yes? This is not news, right? Yes?
We use the Wronskian determinant for this method.
The Wronskian?
Or Wronskian determinant.
To solve what? Solve the linear
Second degree differential equations. We have the first solution, and we use the Wronskian to find the second one.
For this one?
Yeah.
Oh, yeah, to find the particular solution? Yeah. Yes, we can use that. We can take that level of sophistication. I will try to not do that. I'll show you how to, but yes, that would be the way to solve it with the Wronskian. But I'll show you that it can be. So any differential equation that is inhomogeneous. This is an inhomogeneous differential equation. Is the solution to the inhomogeneous equation is the particular solution plus the homogeneous solution, right? So the homogeneous solution for x2 will be the same as the homogeneous solution for x1, yeah? But the particular solution is determined by how x1 looks like, yeah? So that's the one we are aiming at, okay? And yes, you need the Wronskian to find that particular solution. But we'll take a shortcut. Okay, so everybody agrees with this solution, right? Now, I'm going to imagine that I have set my oscillator, like the pendulum, such that the amplitude, at time t equals 0, it has a finite amplitude and no velocity, okay? I can always fix my origin of time, right? If say initially has an amplitude and a velocity, then I can always go back in time or forward in time and select that as my initial time such that, say, I have only an initial amplitude and 0 velocity. So in that case, the phase is 0 for that case. So let me take my phase is a measure or when in time I'm picking to look at the system. Yes? So let me take the phase that is 0. Why? Because algebraically, for the problem that I want to solve and what I want to exhibit, that's the most convenient thing. So then what happens? Well, x1 cubed is equal then to a cubed cosine cube of omega t. Yeah? Which using trigonometric identities, this guy here is equal to 3/4 of cosine omega naught t plus 1/4 of cosine 3 omega naught t. Okay. So, excuse me, there is an a cube multiplying both of them, a cube. Okay. So just as if you want to get to that expression, just remember that cosine cube is cosine times cosine square, and cosine square is 1/2 cosine 2 omega plus 1/2. and then you just keep doing that multiplication and get the cosine of the product. The product of two cosines can be expressed in terms of the sums of the cosine of the sum and the cosine of the difference, and so on and so forth. So you can get here by trigonometric relationships. Okay, so no mystery there, right? Now, this is what makes the second order equation. This is on the right hand side of the second order equation. So when we look at this second order equation, we are looking at this guy, x2 double dot plus omega square x2 equals alpha a cube times 3/4 cosine omega naught t plus 1/4 cosine 3 omega naught t. Now, so this is a differential equation, inhomogeneous differential equation, and we are interested in the particular solution because that's the solution that is generated by the behavior of the system, by the linear behavior of the system. The homogeneous solution to this equation is of no interest because it reproduces the same term that we already have. So we are looking at how nonlinearities correct or modify the linear behavior, and we are doing that by iteration. So notice that so we are exclusively interested in the particular solution. We are interested in the solutions where we have the harmonic oscillator equation on the right hand side and something that looks like a forcing term on the right hand side. Yeah? Yeah, this is, we are driving with a force cosine omega t and a forcing term cosine 3 omega t, 3 omega naught t. Now, do you recognize a problem with this? The first term in particular, we have a forcing term that goes as cosine omega naught t. That's so we have a harmonic oscillator that is being driven by an external force. That's how this term looks like. An external force that is oscillating at the same frequency as the natural frequency of the oscillator. What is that called? Resonance. We have a resonance term. So what happens at resonance? The amplitude is the maximum, right? But the amplitude is the maximum at resonance if we have also a damping term. Do we have a damping term here? No. So what do you think the amplitude is going to be at resonance if we don't have a damping term? Infinite. It is infinite. So let's there is of course going to be a response at cosine 3 omega naught t. That is we can extract that solution. The response at cosine 3 omega naught t is not going to be resonant because if you write x2 as with a term that has cosine 3 omega naught t, you're going to have a way to balance the two sides of the equation as far as that term is concerned. So let me just do it just for kicks. So x2 is going to have, one of the solutions for x2 is going to be some amplitude b cosine 3 omega naught t. So if I take this and plug it on the left hand side of the equation, I'm going to have b minus 9 omega naught square b cosine 3 omega naught t, right? And then the second term is going to be plus omega naught square cos b cosine omega naught 3 omega naught t. And then on the right hand side I have a term that looks like alpha a cube divided by 4 cosine 3 omega naught t. So it's just for me this problem becomes very easy, just a matter of matching b with a, right? Notice that this is the same thing as what? This is the same thing as minus 8 omega naught square b cosine 3 omega naught t. equal to that. So that tells me that then B, that tells me that then B, because I have the same dependence on both sides, cosine omega, 3 omega naught t, cosine 3 omega naught t. So obviously B is equal to minus alpha a square over 32 omega naught square. If I select B to be that, then I have a matching of the right-hand side and the left-hand side of my equation. Okay?
A cubed or A squared?
A cube. Yes, A cube. Thank you. It's A cube. Okay? Now, that's the way I deal with the cosine 3 omega naught t case. I cannot do the same thing with the cosine omega naught t term. Okay? Imagine, let's go through the mechanics again. So if I do now this, then I want to have the first term is going to produce a minus omega naught square b cosine 3 omega naught t. Yes? Plus the second term is going to be omega naught square b cosine omega naught t equals, to match the term, alpha a cube over 3 alpha a cube over 4 cosine omega naught t. The only way that these two can match is if B is infinite. Yes? Can you see that? Because I have this term and that term are the same term. One is a negative term, the other is a positive term. So I would have B being multiplied by 0 times 3 cosine omega t. So the only way that the left-hand side is equal to the right-hand side is if B is equal to infinity, if I choose this solution, which is actually what is going to happen. So the particular solution actually is achieved this other way. To have a solution that doesn't blow up, where the coefficient is constant, then we need something like this, that x2, that part of x2 rather, is something that looks like this. Some term, let me call it C, times t sine omega naught t. If you pick that as the particular solution, then this is what happens. Take that guy, then shove it into the left-hand side. The first term, there are two terms coming out from, when I take the second derivative, and this is my solution, there are going to be two terms that come out. One is minus omega naught square ct sine omega naught t. That's my first term. And then I have plus 2c cosine omega naught t. So this guy is equal to the second derivative of that guy. And then I have the other term. I have plus omega naught square c t sine omega naught t. I'm just shoving in what x2 looks like. And then on the right-hand side of the equation, I have that term that goes as cosine omega t. I have alpha a cube, rather 3 over 4 cosine omega naught t. Now, notice that this guy cancels with that guy, and I have a match. I have a match. Cosine omega naught t on one side, cosine omega naught t. And then I can conclude that C is equal to 3 alpha. Excuse me, I forgot to put an omega naught here. Omega naught right there. 3 alpha a cube over 8 omega naught. That's the value of the constant that solves the problem. But now, look what is going on. The solution to match this term, to find the particular solution that matches this term over here, the particular solution to x2 that matches the inhomogeneous term cosine omega naught t, goes as t sine omega naught t. So over time, the amplitude of the second order term is going to grow, right? That's a problem, isn't it? Because we started by saying that x2, the magnitude of x2 is much less than the magnitude of x1. But over time, the magnitude of x2 is going to get big. It's going to be, at very long times, after a very long time, it's going to get really huge. So that this assumption is immediately violated. That is a minor thing, by the way, that we violate the assumption. The bigger problem is that energy is not conserved. We have an energy conserving system. There is no energy coming in or leaving out here. There is no dissipation or drive in this equation. But the linear dependence in time tells us that the energy of the system is actually not being conserved. Energy is growing in the system. That is physically impossible. Mathematically, we have violated this condition. Physically, we violated the first law of thermodynamics. We cannot do that we cannot do that. Not in this department. Maybe in operation research or in another department they can violate that, but not here. Okay? Anyway.
You can leave that in. Gene, you can leave that in.
Anyway, so there was a problem here. And the problem actually, the resolution to that was something that I said right at the beginning. Right at the beginning, I said that if I look at the pendulum and I look at small amplitudes of oscillation of the pendulum, the time it takes to go one full cycle it depends on the amplitude. Larger amplitudes, the time it takes to complete one full cycle is going to be longer than the time it takes to complete a full cycle for a smaller amplitude. Believe that? Let's try to do the experiment, okay? We are equipped to do that. I have a timer here. And so obviously the way to do this experiment is not to time one cycle, but to time many cycles, right? And a large number, but the larger the number, the more reliable our number is going to be. And the more trust you're going to have in me counting, okay? Because I'm going to be doing two things. I'm going to be counting and pushing a button. So that takes a coordination and mental coordination that I don't quite have. But if I count several cycles, then you are going to believe me. So let's try the problem of small amplitudes. Let's try this problem, okay? And I'm going to start at the swing right there. And oh shoot, sorry. Let me start again because I forgot how many cycles I had. So let me start again. Right here, and I'm going to start at the swing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, obviously, I wanted to start at the extreme of the swing because that's when the pendulum spends the most time, right? That the velocity comes to zero. So the pendulum is, if I count in the middle, I really need to be very attentive to them. That's the least amount of time spent. So for 10 oscillations, I have 16.88 seconds. Okay, let's write that number just to make sure. 16.88. for this smaller amplitude. Now let me do the larger amplitude, that one. Okay? So I'm gonna reset it. So sorry, I need to reset it and then start counting. 1, 2, 3, 4, 5. Oops. That's a bad problem. So let me stop it. We're gonna get to that actually. That's a really nice demo. But let me first do the simple one, just the counting. So let me try to be straight here. So I'm gonna let it go from here, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 17.85. Notice that the difference in time is not humongous, right? It's like, wow, what a big effect. That's what I told you. It's not a big effect, but it's actually a measurable effect. So thinking about iterations, it was not a bad idea if we do it for a short amount of time. You know, if we don't spend much time, then our iteration solution is okay. But for a longer time, the iteration solution is not okay. And again, this is not quite, this is not a very simple pendulum because I'm not releasing it. It's not quite planar. You notice it was not quite planar. There was a little bit of ellipticity to the trajectory. And so we're going to come back to that particular demo. That's a very interesting demo. So what is the lesson here? The lesson is that when I write the solution for x1 like this, to look like omega naught t, cosine omega naught t, I'm making a fundamental mistake physically, because the frequency omega naught is the frequency for small amplitude, for an infinitesimally small amplitude of oscillations of the pendulum or the oscillator. Omega naught, the omega naught would correspond to omega naught. There would correspond a period. The period of oscillation for omega naught would be 2 pi over omega naught. But the period, again we say, the period depends on the amplitude. Larger amplitude in the case of the pendulum has longer periods. So what I have to build in my formulation to do the problem correctly is that dependence of the frequency on amplitude, of the period on amplitude. So this cannot be my starting point. So let me go back and start again. I'm going to go back and do this, erase my... That's not what I want. That's not... I want to have this x. I'm going to have it some amplitude A. The pendulum is oscillating at some amplitude A. And what I'm going to do now is a very simple substitution. I'm going to I'm going to make a very simple substitution, which is the following. I'm going to do A cosine not omega naught t. I'm going to call it omega. Okay? Omega t. And again, I'm thinking that I start with a problem where time can be reset so that the phase is 0 when I reset my time. So notice that I have an omega, over here I have an omega naught. In the iteration problem, I have an omega naught. I'm not going to do that mistake. I think that's the root of my problem, that I didn't use the right physics into the solution, or into the ansatz solution at the beginning. What else? What else did we see we saw in but the iteration problem taught us something very valuable, and that is that the solution, the correction to the linear problem brings harmonics, right? We had, remember in the x2 equation, we had a cosine omega naught t, and we have a cosine 3 omega naught t. Remember that? So the correction, nonlinearities are gonna bring in anharmonic behavior. We have still periodic, the behavior is still gonna be periodic because there is a fixed period of oscillation, but it's not gonna be harmonic. There are gonna be multiple harmonic components to the behavior. The cosine omega t, cosine 3 omega t. So let me go ahead and write that down too. I'm gonna write b cosine 3 omega t. And then there are other terms. That's gonna be the way I approach this problem. What is omega? To be determined. That's the thing. We are gonna determine it by just taking that solution and plugging it in. And we are gonna do this by what is called a method of harmonic balance, where what I have on the left-hand side matches what I have on the right-hand side, or I make it, I force it to match. So I have a cosine omega t term on the right-hand side. I'm going to make that match with a cosine omega t term on the right-hand side. So I'm going to be doing the harmonic balance method. That's what it's called. Where my starting point is an input in physics. Omega is not omega naught. It's to be determined. And we are going to determine by balancing the harmonics. So there are in this particular equation, by the way, the fact that this has a cubic nonlinearity makes that choice correct. That the solution should be omega t, 3 omega t, 5 omega t. So when we have a cubic nonlinearity, the harmonics, there are going to be harmonics in the solution, and those harmonics are going to be odd harmonics. If we had an x squared instead of an x cubed, then the solution would include all harmonics, not only the odd ones, but it would be the first harmonic, the second harmonic, third, and on forth. Over here we have the first, the third, the fifth, and all that. So the most general solution is going to be a solution that includes all odd harmonics. As it turns out, solving the problem where the nonlinearity is cubic is simpler than solving the problem where the nonlinearity is quadratic. When the nonlinearity is quadratic, it requires extra terms. And so what I want to show you right now, the simple problem, how to do the simple problem, the cubic nonlinearity with the harmonic balance terms. So we're gonna do that. We're gonna take that as our solution. We don't know what A is given, but we don't know what B is. A, say, is the amplitude of the pendulum, okay? And then based on that, we're going to determine what B is. And we are also going to determine what omega is. So on the right-hand side, or rather on the left-hand side, I have what? I have the first term is going to give me minus A omega squared cosine omega t. I'm going to take the second term as well. I'm going to have minus b, rather 9b omega squared cosine 3 omega t. So these two correspond to the derivatives, the second derivative of the first term. Of course, I have other terms. So let me include them like so. So this is the second derivative of my solution. Then I have the next term, omega naught squared, okay, times A cosine omega t plus B cosine 3 omega t, etc., equals to the cube of that solution. So I'm going to write the first two terms, and then I'm going to stop there. Okay, writing the first, beyond, it's just extra. So I'm going to write alpha. Then I have the first term is cubic, a cubed cosine 3 omega, cosine omega t cubed. Okay, and then I have plus 3 times a square b cosine cosine square omega t times cosine 3 omega t plus other terms. Okay, so I'm gonna stop at that one. So the harmonic balance method consists again on matching coefficients of each harmonic term to each other. The coefficients of cosine omega t on one side of the equation are equal to the coefficients of cosine omega t on the other side of the equation. That's all, right? So what do we have as cosine omega t? We have this term and we have that term. So let's match those. The cosine omega t terms. They are on the left-hand side is a omega minus a omega squared plus a omega naught squared. So let me write it as this. I'm going to write it as a omega naught squared minus omega squared. That is the right-hand side for, the left-hand side rather, for the terms that go as cosine omega t. Okay? On the right-hand side, I'm going to have, remember, this guy produces a cosine omega t term. Okay? Actually, this guy here is the same thing as 3/4. Sorry, I have to go back and use my 3/4, right? Cosine omega t plus 1/4 cosine 3 omega t. So that's from the first term. From this other term, we also have a cosine omega t term. Okay, just look at it. This guy is going to have a term that goes as cosine 2 omega t and a term that goes as, right? So we have cosine square omega t is 1/2 cosine 2 omega t plus 1/2. Yes? And then, but it's been multiplied by cosine 3 omega t. So the term, this term that goes as 1/2 ends up being cosine 3 omega t, right? But this term that has the cosine 2 omega t, now cosine 2 omega t times cosine 3 omega t, that is equal to 1/2 cosine of the sum plus cosine of the difference. And that has cosine omega t, right? So, but this is the good news. It's not that, wow, then I have to look at all the harmonics because the next term, the one that has cosine 5 omega t, is also going to bring down a cosine omega t term. My God, this is a never-ending story, right? But this is where we enter as physicists. We make approximations. And the approximation that we are going to make is the one that we made originally in the iterative term. We're going to say that A is much bigger than B. And B is much bigger than the next order term as well. So the cosine omega t term that is produced over here is of lesser order than the term we have here, because A is much bigger, is much less than B. So the only term that we really need to keep is the one that comes from the first cube, right? That is, this guy is approximately equal to alpha a cube 3 alpha A cubed over 4. And then there is garbage. There are terms that are order B, okay, or let me call them order A square B, okay, which are smaller than this term, because you would have terms that go as, so we're comparing A cubed to A square B. A cubed, how does it compare to A square B? Well, first of all, this drops compared to that, and so this is much bigger than that, right? So these corrections are small compared to this one. So that's why we are saying this guy is to good approximation is actually they both are equal. Then you see what happened? Now we have a solution for omega. Omega, which is an unknown, now is known because this amplitude falls, drops off, and so we have that the difference in frequency goes as, the difference in the square of the frequency goes as the square of the amplitude. So this is where we're saying omega naught square minus omega square is equal to 3 alpha A square over 4. The frequency depends on amplitude. The frequency that we have depends on amplitude. This omega naught is an intrinsic property of the system, depends on is the linear term. But the frequency of nonlinear oscillations depends on amplitude, and depends on amplitude as A square. So tomorrow we'll come back to this result, and we'll do a couple of demos and get very acquainted with this particular answer. Okay.